Okay, so I'm going to talk today about our next lesson in Unit 2B. It's linear approximation. And honestly, guys, this is going to be really, it's going to seem like nothing new. It's really just tangent line approximation. So I got a one up here. You can try this on your own. Like to do it in class together as usual. So it's dealing with implicit differentiation. It's just practicing that and going back to that idea. So you're welcome to try this problem. It's from a free response way back when. I can't remember what year. So see if you can do it. But otherwise, let's move on to the lesson. All right. So suppose you're let's look at an example that kind of introduces this idea of linear approximation. And this is a really basic, silly example to kind of help us picture what's going on here. So suppose you are you're cooking a turkey. Initially, the oven's temperature is 50 degrees. After an hour, the temperature is 93 degrees. At 2 hours, the temperature is 129 degrees. What is the temperature going to be after 3 hours? So the thing with linear approximation is it's just that. It's an approximation. It's not exact. And it's literally using a line to predict it. Okay? You might remember this kind of being along the lines of line of best fit. You've done linear approximation in that sense of the word way back when. It's not the same. We're using tangent lines now, but it's pretty much doing the same thing. So like for instance, if I were to graph this below here, it says, let's see, initially at time equals 0, we'll call this time, and this temperature. And it looks like at time equals 0, just say that maybe, I don't know, this is 50, we'll go up another 3, that's 100, we'll go up another 3, maybe that's 150. And it says initially we're at a temperature of 0, then after an hour, I'll label it like this, maybe 1, 2, 3, whatever. So initially we're at 50. After an hour, we're at 93, which is about right here. And time 2 hours, we're at 129. So where would that be? This is 100, 125 in the middle, 129 is like right here. And it wants us to figure out what the temperature is going to be at time equals 3. Well, I don't have an equation. I have no idea. I'm purely going off of a guess. And that's all approximating is just a guess, but it's going to be an educated guess. Okay? I mean, this isn't perfect. It's kind of like a line of best fit here. But if I were to follow along this lineage here, it would be somewhere right, somewhere right here. Which, I don't know, let's see. I mean, it looks like, you know, up right here would be about 175. I'd say that's about 175, 170. We'll just say 175 degrees. And I mean, that's all we're doing, okay? But we're going to be doing it with tangent lines. So let's explain with this next example. Because we use the tangent line at a, f of a, as an approximation to the curve y equals f of x when x is near a. All right? The tangent lines have got to be close to a. Otherwise, it wouldn't make much sense. We'll see that graphically in a second. So it must be very close to a. Now, the equation of this tangent line is given like this. Notice how, I mean, that's exactly how we write it. We just write it with f of a over on the left side, but they just went ahead and brought it to the right side. They're the same exact dang thing. Notice how a linear approximation is nothing more than a tangent line. That's all it is. So we're just using a tangent line or linear approximation or a tangent line approximation at a value close to the tangent point. Okay? So the linear function whose graph is the tangent line, is this tangent line, that is, and they use L of x for linear approximation, but it's just the same exact thing as a tangent line. And this is called the linearization of f at a. We're pretty much linearizing a function. So let me give you an example, like graphically. Like, I mean, let's say like that's my graph. Something that looks like that. Let's say like right here at A, I have a tangent line. Looks like that. Now let's say maybe I don't have a calculator, maybe there's some complications, but let's say I want to know the value of A. Well, I can't find A from the curve. Let's say for whatever reason it's a really complicated equation. But if I can find a line, a tangent line, wouldn't you agree that like any points that I approximated around this point would be easy to find? Like this point and this point are really close together. This point and this, like I can use this line to estimate or approximate any point around A. I'm not going to use this tangent line to approximate this point over here because it's nowhere near it. But I can use the tangent line to approximate points around the tangent line. So for instance, let's say like A is 2. Let's say we know, f of 2. Okay? But let's say like maybe I want f of 2.1. Well, decimals are usually annoying to plug into calculators, stuff like, or into equations. Maybe we don't have a calculator. Maybe if I can create a tangent line, 2.1 on this curve is going to be really close to 2.1 on the line. So I think it's going to be a pretty good approximation. That's kind of the idea here. Let's try a couple examples. It's not the craziest stuff. Again, it's just tangent line. Okay. So let me see. Perfect. It says let f of x be the square root of x, which we know looks like that. Okay, I mean it's just that it's a function that's flattening off as it goes to infinity. It says find the linear approximation, which is another way of saying tangent line at A. So it says find the linear approximation to f of x at x equals 4. So all that's saying to do is find the tangent line at x equals 4, which is nothing too crazy at all. Okay. Remember, for a tangent line, we need a few points. We need a and f of a, or x and y, and we need to know f prime of a, so the slope at a. In this case, it's 4. So we'll start by finding the derivative. F prime of x is equal to, we've taken the derivative of the square root of x so many times, it's going to be 1/2 x to the negative 1/2 power. Okay. All right, so my point in this case for the slope, f prime of 4, is 1/2 square root of 4, which is just 1/4. All right. And the point in this case is 4, comma, and if I plug 4 into the square root of x, I get 2. So my tangent line, and the way that I always told you to write tangent line, is y minus y, or y minus 2, equals 1/4, and then x minus 4. Now, the linearization, or the linear approximation, is just that. But they just get y by itself. That's the only difference, is y equals, I'll bring 2 to the other side. And this right here is the linear approximation, all right, of f of x at x equals 4. Now, I want us to understand what this means. So if I go on my graph, 1, 2, 3, 4, it's this point right here. You can see it even has a slope of about 1/4, just like we found. It looks like this. There we go. Now, the whole idea of linear approximation is I have a line that shares the same point at 4. They both share the point 4, 2. But let's say I wanted to know, maybe, I'll give an example here. What if I wanted to know the value at 4.1 of the square root of that, like the square root of 4.1, which is right here on my curve? Wouldn't you agree that the linear approximation, or the tangent line that's really close to 4, is going to be a pretty close approximation? And it's a lot easier to approximate by plugging into a line than it is to any other function. So that's kind of the idea, is we use a tangent line to approximate points around the tangent point. So a follow-up question could be something like this. I could say in part B here, maybe, let's say that x equals 4.1. Approximate f of 4.1, which is the same thing as the square root of 4.1. Now let's assume we don't have a calculator and we can't actually find that answer. Then a linear approximation is something I can use to approximate the square root of 4.1 because I have no idea how to take the square root of that. So what we could use is y equals 2 plus 1/4, and instead of x we could do 4.1 minus 4. And we could probably simplify this down pretty nice. So that's 2 plus 1/4, and then maybe that's 4.1 minus 4 is 0.1. And to maybe help me with this process here, I could change that to maybe a fraction if I wanted to get an exact approximation here. Let's keep going. 2 plus 1/40, which if I really want to get technical here, that could be 80/40 plus 1/40 is 81/40. So there's my approximation of 4.1 using a tangent line close to 4. All right? Again, not the most terrible thing in the world. Let's see. 81/40. Now let's actually bring our calculator into play here. 81/40 is the same thing as 2.025. So that's my approximation of the square root of 4.1. I'm curious what the square root of 4.1 is in my calculator. It's 2.0248, blah, 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 blah. So you see that the linear approximation and the actual value of the square root of 4.1 are pretty dang close. And that's all this is an approximation if we don't have a calculator. Okay. Let's try another example. I'll just do these 2 more slides. We'll call it after that. Okay. Cool. It says find the linear approximation to 5x cubed plus 6x at x equals 2. That's just a fancy way of saying find the tangent line at x equals 2. And that's what we're going to do. Remember, for any tangent line, we need a point and we need a slope. So we need these 3 numbers. Let's start with the point. Point is 2, comma. If I plug 2 into this mess right here, that's 2 cubed is 8 times 5 is 40 plus 12. So I believe this is 52. And you can check my math on that if you want. Now the slope, so f prime of x equals 15x squared plus 6. And if I plug 2 into this, 2 squared plus 6. What do I get? 66, I think. So the linear approximation in this case is, and I'll write this in purple, y minus 52 equals, and then my slope was 66, and then x minus 2. Okay. All right. Now, that's my tangent line. I guess if you want to write it in terms of a linear approximation, so we can approximate any value close to 2, we can just get y by itself. So, I mean, graphically, let's look at this. I mean, we've seen this before. We've done tangent line graphs before. 5x cubed plus 6x. And then the linear approximation was 52 plus 66, x minus 2. 52 plus 66, x minus 2. Now, it's a very steep slope, so I'm going to zoom out a little bit. My goodness, that's going to be really hard to see graphically, but you can see, I mean, if I zoom in right here at 2, look how close this graph is to the actual function. So 2 is like right, oh God, here, I gotta keep going down. There, that's what they intersect, 252. Now look at this tangent line. Look how close it is to the actual function. So if I were to choose any point around this tangent point, it's going to be a pretty close approximation to what the actual value in the curve is. So, and again, the reason is because doing linear functions is a lot easier than sometimes doing other operations. So let's keep that in mind. Like right here, okay, for instance, 1.98 for the function in example 2. So if I'm approximating that, I don't want to plug 1.98 into that without a calculator because I don't want to cube it and multiply. That's annoying. Let's try it in a linear approximation. So that's y equals, and again, this is going to be approximate. So y approximately equals 52 plus 66, and instead of x, we'll plug in 1.98 minus 2. And the reason this is so easy sometimes is because the decimal is never going to be bad. Like, that's negative 0.02. And we can usually deal with those fractions a lot easier. So that's 52 plus 66 times negative 2 over 100. 2 over 100. And we can multiply, so I mean we can kind of keep going with this. We could do 52 plus 66 times negative 2 is negative 132 over 100. I can get a common denominator. I can say maybe 5200 over 100 plus negative 132 over 100, and finally combine those together. So y is approximately equal to, what's that? 5,068? 5,068 over 100. Which now if I bring this into the calculator, all right, if I actually do 5068 divided by 100, just curious now, I get 50.68. So I'm assuming, like, if I plug this back into the original equation, like if I actually found f of 1.98 and I did have a calculator, if I actually found that exact value, I'm curious what I'd get. Do it right now. The actual value is 50.69196, and that is a pretty dang close approximation. So tangent line is nothing more than approximating. Okay. All right, I got one more, and then we'll call it. One more, then we'll call it. This is approximate the square root of 66 using a linear approximation. So this problem is a little unique because I'm not telling you an explicit equation. So how can I approximate the square root of 66 using a linear approximation? Well, the square root of 66, I don't know that. I'm trying to approximate that. I can't figure that out. Is there a value close to that I do know the square root of? I'm sure you're already kind of recognizing that, yeah, what if I use a linear approximation at maybe x equals 64? Because I can take the square root of 64, and 66 is close enough to that. So then what equation am I looking at? What is f of x in this case? The square root of x. If I can get a tangent line at x equals 64, which because that's an easy number to deal with square roots, then I can approximate the square root of 66 all day long. All right, so let's think about this. So my point is going to be 64, comma, and the square root of 64 is 8. Yeah, 8. Brain fart. And then now if I do f prime of x, again, that's 1/2 x to the negative 1/2. And if I plug 64 into that to get my slope, I get 1 over 2 times 8, or 1 over 16. So my tangent line is going to be y minus 8 equals My slope is 1 over 16, and then x minus 64. And I guess if I want a linearization of that, I mean, it's helpful to write it where y is by itself. And there we go. So I didn't do any new math, guys. All I did was just find the tangent line at 64. Now let's think about what this looks like graphically. If I were to graph this, I mean, here's the square root of x. What the heck? Square root of x. There it is. And I know the point, like if I go over to 8, or I'm sorry, 64, I know the square root of 64 is 8. But what about the square root of 66? Okay. Well, if I plug in that linear approximation, which was y equals, I already forgot. Oh, yeah. 8 plus 1 divided by 16, x minus 64. Look how I got a tangent line right here. So I'll be able to approximate 66 really close by looking at the linearization. It's going to be a really close approximation. So let's do that. Let's plug in 66 into this and see what it is. Y equals 8 plus 1/16, and then 66 minus 64. And this is easy to compute, right? 8 plus 1 over 16 times 2. And that is 8 plus 1 over 8. Or I could just say 64 over 8 plus 1 over 8, which is 65 over 8. That is my approximated value of the square root of, so I'm saying basically that the square root of 66 is approximately 65 over 8. That is what the linear approximation found. Now the actual value, I took the square root of 66 in my calculator. The actual value for the square root of 66 is equal to 8.12403, blah, 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 which is pretty dang close to what 65 over 8 is. Okay. So linearization is nothing crazy, and sometimes it's annoying because, well, I approximate when I have a calculator, but the option is there if we ever need it. Okay. All right, that's all I wanted to go over. So tomorrow I'll re-explain some of this. Go into a couple new things, but for the most part, linearization is where it's at. So, thank you guys. Y'all have a great day.